Again, welcome to operating system called CS332 class. And in this lectures, we're going to cover the concept of memory partitioning and also paging. So these lectures cover our course textbook, chapter 7. So our main objective again is to go through memory partitioning. We're going to talk about the phase partitioning, dynamic partitioning, and also border system, relocation, paging, and segmentation. Normally, paging and segmentation involve in a virtual memory concept, which we are going to cover that in chapter 8, hopefully next week. So the principal operation of memory management, as we said, is always to bring processes into main memory for execution by the processor. And also in most modern multi-programming systems, this involves a very sophisticated scheme known as virtual memory. So virtual memory in turn is based on the use of one of or the following two methods we mentioned, which is the segmentation and paging. But before we look at segmentation and paging, we shall go through the techniques we know as memory partitioning. Memory partitioning doesn't involve, bringing a requirement of a virtual memory concept. So memory management, again, goal is to bring process into main memory, as we said, for execution by the processor. It normally involves virtual memory, which is based on segmentation paging. But we can also use the partition method, which normally is used in several variations in some obsolete operating systems. So partition is our old method of managing memory, and it doesn't involve virtual memory. So before we move on to virtual memory, which is chapter 8, we shall go through the concept of, again, memory partition. So these are some few techniques, as we mentioned. So we have the description, the strength, and also the weaknesses. So let's see the first method, which is the phase partitioning. So phase partitioning means the memory is divided into a number of static partition at a system generation time. So a process may load it into the partition of equal or greater size. So the whole concept that phase means it doesn't change, the size is constant. It's the same concept as saying an array with linked list. We know an array, when we declare an array, we have to specify the size. So it's a fixed size. We don't change it during the running time of the program. But with linked list, we say it's dynamic concept, which means we can change the size while the program is running. So the same thing applies here. Phase partition means the main memory is divided into a number of static, doesn't change, partitions at system generation time. So a process may be loaded into partition of equal or greater size. Now, what is the advantage of this method? It's very simple to implement. Very simple to implement, related operating system overhead. But again, it's not efficient. Same as we said, array is not efficient, because if we declare higher size and large size, and we didn't use most of them, then we waste resources. Or sometimes we may declare it's not enough, then the program cannot run because it can't, again, store all the data in the array. So it's an inefficient use of memory due to the internal fragmentation, which is the maximum number of active process is phase. Now, dynamic partition is more better, but these partitions are created dynamically, which means the size of the memory. Again, partition concept is dividing. So if you say we partition our memory, it means we are dividing into some. Excuse me. Which means we are divided into some specific size. So dynamic partition, we say partitions are created dynamically so that each process is loaded into a partition of exactly the same size as that process. So here there's no any internal fragmentation, and it's more efficient use of the main memory. Advantages is inefficient use of processor due to the need for compaction to counter external fragmentation. Another method is simple paging. So we have paging and segmentation, which involve normally virtual memory. Simple paging, not really. So we say simple paging, the main memory is divided into a number of equal size frames, and each process is divided into a number of equal size pages of the same length as the frame. So a process is loaded by loading all of its pages into a variable, not necessarily contiguous frames. Advantage, again, is same concept. There's no any external fragmentation. Disadvantage is a small amount of internal fragmentation. Then we have the simple segmentation. Here we say each process is divided into a number of segments. So the process is loaded by loading all of its segments into a dynamic partitioning that need to be contiguous. Also, there's no internal fragmentation for this. And this also improves the memory utilization and also reduce the overhead comparing to dynamic partitioning. And we have the external fragmentation, which is the disadvantage. So in our next chapter, we're going to discuss about virtual memory paging and virtual memory segmentation. So virtual memory paging, as with simple paging, this time the difference is that it is not necessary to load all of the pages of a process. So non-resident pages that are needed are brought into the later automatically. So this one also the same concept. There's no external fragmentation. And also the overhead of complex memory management is the main thing is the overhead of complex memory. And the same thing applies to virtual memory segmentation, the overhead complex memory management. Because implementation of virtual memory needs a lot of overhead, communication, etc. So virtual memory segmentation, as with the simple segmentation, the same except that it is not necessary to load all of the segments of process. Non-resident segments that are needed are brought in later automatically. So these are all the techniques we are going to learn in both chapter 7 and 8 about memory management. So this session, we're going to learn the partitioning, memory partitioning, both the phase and dynamic, and also simple paging and simple segmentation, which normally is not involved, excuse me, it's not involved virtual memory. So example given here, we have an equal size partitioning and also unequal size partitioning. So this would be an example of a phase partitioning for 64-byte memory. So in most scheme for memory management, we can assume that the operating system occupies some phase portion of main memory, and that the rest of the main memory is available for use by multiple processes. So the simplest scheme for managing this available memory is to partition it into a region with phase boundary, and that's what we have here. So the partition size shows the example of two alternatives for phase partitioning. The first one, the left side, one possibility is to make use of equal size partition. So the first one is equal size, and the second one is unequal size. So in the case of equal size, any process whose size is less than or equal to the partition size can be loaded into any available partition. since they are all equal size, any data or any process can be loaded to any variable. Now, the next option, if all partitions are full and no process is in the ready or running state, then the operating system can swipe or process out of any of the partitions and load in another process so that there is some work for the process to do. So the disadvantage is a program may be too big to fit in a partition, especially the fit size. Program needs to be designed with the use of overlays. So main memory utilization here is inefficient. Any program, regardless of size, can occupy an entire partition. So when a module is needed, that is not present, the user's program must load that module into the program's partitions, then overlaying whatever programs or data are there. So here we say the main memory utilization is extremely inefficient for the face size. So any process again, or any program, no matter how small, occupies an entire partition. And also in our example, there may be program whose length is less than 2 megabytes, yet it occupies an 8 megabyte partition. So whenever it is swiped in, this phenomena in which there is a wasted space internally to the partition due to the fact that the block of data loaded is smaller than the partition is referred to as the internal fragmentation. So internal fragmentation means wasted space due to the block of data loaded being smaller than the partition. Now we have what we call the placement algorithm. So with again equal size partition, the placement of process in memory is trivial. As long as there's any variable partition, a process can be loaded into that partition. Now, because all partitions are of equal size, it does not matter which partition is used. Now, if all partitions are occupied with process that are not ready to run, then one of these processes must be swiped out to make a room for a new process. Then which one to swipe out is a scheduled decision. Then we may discuss this again in the future. Also, with unequal size partition, there are two possible ways to assign process to partition. The simplest way is to assign each process to the smallest partition within which it will fit. In this case, a scheduling queue is needed for each partition to hold swap out process destined for that partition. And that's the concept here. So we can see in our left diagram, we have new processes and they will be assigned to different partition. Again, this can be based on the size. This is on equal partition. So advantage of this approach, again, as we can see in the figure, left side A, the advantage is that the process are always assigned in such a way as to, again, minimize the memory within partition. And this is the concept of internal fragmentation again. Now, with equal partition, it doesn't matter. But with unequal partition, we want to assign a process that is larger into the larger partition, that is smaller into the smaller partition. So So although the technique seems optimum from the point of view of an individual partition, it is not optimum from the point of view of the system as a whole. So in our right figure, for example, consider a case in which there are no process with a size between 12 to 16 at certain point in time. In that case, 16 megabyte partition will remain unused, even though some smaller could have been assigned to it. So that's the preferable approach will be to employ a single queue for all process. So when it comes to load a process into main memory, the smallest available partition that will hold the process is selected. Now, if all partitions are occupied, then swapping decision must be made. Preferences also must be given to swapping out of the smallest partition that hold the incoming process. Now, the disadvantage is that the number of partitions specified at system generation time limits the number of active processes in the system. So small job will not utilize partition space efficiently. So let's move to the concept of a dynamic partition. So partition of a very different size. So partition of a variable length and number, different size. Now, because partition sizes are preset at system generation time, small job will not utilize partition space efficiently. So now to overcome some of these difficulties with phase partitioning, an approach known as dynamic partitioning was developed. Again, this approach has been supplanted by more sophisticated memory management techniques. An important operating system that used these techniques was the IBM mainframe operating system. And that was the OS/MVT, multi-programming with variable number of tasks. So with, again, dynamic OS/M, that's again multi-programming with a variable number of tasks. Again, with dynamic partitioning, the partitions are of variable length and number. When a process is brought into main memory, it is allocated exactly as much memory as it is required and no more. So this example we have using 64 megabytes of main memory. Initially, the main memory is empty. You can see the main memory is empty. We have 56 megabytes. Then the first three processes are loaded in, where the operating system ends and occupies just enough space for each process. So that's the B, C, D. We have process 1 and 2 and 3 at D. First process 1 is loaded, then process 2, then process 3. This will leave a hole at the end of the memory that's too small for fourth process. So at some point, none of the process in memory is ready. In this case, the operating system swipes out process 2. Let's go back. So in this case, we can see process 2 is swiped out. Which leaves again sufficient room to load a new process. And that will take us to process 4. Still, we have some space, but process 4 is smaller than process 2. So another hole is created. Later, a point is reached in which none of the processes main memory is ready. But process 2 in the ready suspend state is available. But because there's insufficient room in memory for process 2, the operating system swipes process 1 out, and that will be G, and then swipe process 2 back in, and that will take us to B. So again, as this example shows, the method starts out well, but eventually it leads to a situation in which there are a lot of small holes in memory. As time goes on, the memory becomes more and more fragmented. Fragmented means there's hole between the processes space. Then the memory utilization will decrease. So next, again, we're going to talk about dynamic partitioning, which is the external fragmentation. Here we say the memory becomes more and more fragmented, and the concept of a memory, again, utilization. Then compaction is one technique for overcoming external fragmentation. So again, one technique for overcoming external fragmentation is compaction. So from time to time, the OS shift the process so that they are contagious, and so that all of the free memory is together in one block. So we can see examples. So compaction is a technique to overcome external fragmentation. Also, the operating system shift processes so that they are contagious. Free memory is together in one block, and time consuming and waste CPU time. So we have the concept of, again, placement algorithm. First, we should know the best fit. We should know the first fit and also the next fit. So because, again, memory compaction is time consuming, the operating system designer must be clever in deciding how to assign process to memory. Also, how to plug the holes. Now, or when it is time to load or swipe a process into memory, and if there's more than one free block of memory of sufficient size, then the operating system must decide which free block is allocated. Now, the three placement algorithm, as we can see in our screen, that might be considered the best fit, the first fit, and the next fit. Again, all, of course, are limited to choosing among free blocks of main memory that are equal to or so again, all of the costs are limited to choosing from free blocks of main memory that are equal to or larger than the process to be brought. So the best fit chooses the block that is closest in size to the request. And also first fit begins to scan main memory from the beginning and choose the first available block. Choose the next available block data is large enough. So choose the block data that's closest in size to the request. Then the first fit begins to scan memory from the beginning and chooses the first available block that is large enough. Next fit will begins to scan memory from the location of the last placement and chooses the next available block that is large enough. So again, both fixed and dynamic scheme have a drawbacks or disadvantage. And also the figures show here an example of memory configuration after a number of placement and also swapping out operations. So the last block that was used was the 22 megabytes. So you can see so the next is the boarding system. Normally the boarding system comprises of fixed and also dynamic partition scheme. The space available for allocation is treated as a single block, and then the memory blocks are variable of size 2 to the power k, where k will be less than or equal to u and greater than or equal to l. So here we say the memory comprised of fixed dynamic partition scheme, the boarding system. Again, we said the space available for location, allocation is treated as a single block. So 2 to the power L will be smallest size block that is allocated. 2 to the power U will be the largest size block. So this example of a body system. Here we say that the figure gives an example using 1 byte initial block. 1 byte, we see releases the 1 byte. And this is for 100 kilobytes, for which 128 kilobyte block is needed. So again, that's the concept. So the figure gives us an example using 1 megabyte initial block. And the first request A, as we can see, the first request A is for 100 kilobyte, for which 128 block is needed. So we request 100K, but 128 is needed. Then the initial block is divided into 2 512K bodies. So the first of this is divided into 256 kilo bodies, and the first half of this divided into 2, as we can see, 128 kilo bodies. So one of which is allocated to A. The next request B requires 256 blocks. So such a block is already available and is allocated. So the process continues with splitting and coalescing occurring as needed. Now in figure 7-7, it shows again the binary tree representation of body allocation immediately after releasing B requests. So the leaf nodes represent the current partition of the memory. So that's our leaf nodes down there. And we can see the partition 256, 64K, etc. Now, if 2 bodies are leaf node, then at least one must be allocated. Otherwise, they will be coalesced into a larger block. The body system is reasonable, comprised to overcome the disadvantage of both fixed and variable partition schemes. But again, in a contemporary operating system, virtual memory based on paging and segmentation is superior. However, the body system has found application in parallel system as an efficient means of allocation and also leads for parallel system. So the next will be the relocation. So when the first partition scheme is used, we can expect the process will always be assigned to the same partition, but this doesn't happen. So before we consider ways of dealing with shortcomings and partitioning, we must clear up one loose end. which relate to placement of process in memory. Now, when the fixed partition scheme is used, we can expect a process will always be assigned to the same partition. So here we say whichever partition is selected, when a new process is loaded, will always be used to swipe that process back into memory after it has been swiped out. So in that case, a simple relocation loader can be used. So again, in the case of equal size partition and the case of single process queue for unequal size partition, a process may occupy different partitions during the course of its life. Here we say when a process image is first created, it is loaded into some partition main memory. We also have the addressing. We have logical address, relative, and also the physical address. Physical address also called the absolute address. So logical address normally refers to the main memory or the memory location independent of the current assignment of data to memory. And also the relative is a particular example of logical address in which the address is expressed as a location. The location is relative to some known point. Then we have the physical or absolute. The physical will be the actual location in the main memory. So next we go to the paging. Again, this is simple paging, a little bit different from the virtual paging. So here we say the partitioning memory, we partition memory into equal field size chunks that are relatively small. So process is also divided into small field size chunks of the same process. So we have paging. Pages means chunks of process, and frames means variable chunks of memory. So this is an example given to us. So here we can see 15 variable frames, then local process A, then local process B, C, then swipe out B, then local process D. So again, the page table is normally maintained by operating system for each process. Also, it contains the frame location for each page in the process. Also, process must know how to access, processor must know how to access for the current process, also used by processor to produce physical address. So again, this is an example given to us, the data structure for the example of figure 7.9. And also 10. So we continue our example, the 5. Again, pages of process they are loaded into 4, 5, 6, 11, and 12. So again, in our example, we saw this technique. So here A is the partitioning. We have the user process 2700 bytes, and we have the relative address. Second, we have our logical address, and we have 3 different pages. with internal fragmentation also. So you can see our addresses, 16-bit logical address to 16-bit physical address. So the next will be the segmentation. So we continue our example. Segmentation is a program can be divided or subdivided into segments. May vary in length, and there's a maximum length. So addressing normally consists of two parts: segment number and also an offset. Now, segmentation is similar to dynamic partition, and also it eliminates the internal fragmentation. So segmentation, again, usually visible. And here we say a user program can be subdivided using segmentation. And again, in which the program and its associated data are divided into number of segments. So it's not required that all programs of all segments of all programs be of the same length, although there's a maximum segment length. And as with paging, a logical address uses segmentation consists of two parts. So for the purpose of modular programming, the program or the data may be further broken down into multiple segments. Now, the principal inconvenience of this method or the service is that the programmer must be aware of the maximum segment size limitation. We also have the address translation, which is another consequence of unequal size segment, is that there's a simple relationship between logical address and physical address. So the extract the segment numbers as the leftmost n bit of logical address. Then use the segment number as an index into the process segment. Then compare the offset expressed in rightmost n bit to the length of the segment. So that's an example here. And that will be the conclusion. So in this example, we have at least a logical address of 001, 0010, all the way to the end, which is segment number 1. Offset by 752. Suppose that this segment is residing So again, that will be the conclusion of our lectures. And again, wish everybody the best and thank you for your time.